let's unpack this. There is a massive misconception out there about machine learning.
Mm-hmm.
I think when most of us hear ML or, AI, especially with all the hype lately, we picture this absolute wizardry,
Right.
a lone genius in a basement furiously typing on a mechanical keyboard, writing a brilliant algorithm that suddenly wakes up, solves the universe's problems.
And probably writes a symphony on the side. It is very cinematic. And it is almost entirely wrong.
Right. Because today we are diving into the messy, unglamorous, and frankly fascinating reality of what it actually takes to make this stuff work.
We aren't looking at a textbook today.
No, we're looking at a battle plan. We're doing a deep dive into designing machine learning systems by Huyen.
And this is a seminal text for a reason. Chip isn't just an academic theorizing from an ivory tower. She's been in the trenches. She was a LinkedIn top voice in data science back-to-back. She's worked at NVIDIA, Netflix, Snorkel AI. I mean, she operates right at that painful intersection of here's the beautiful math.
And here is why the server just crashed and set off the fire alarm.
Exactly.
And the mission for this deep dive is pretty clear. We aren't talking about the math of the models today. We aren't going to discuss how a neural network weighs neurons or calculates gradients.
No.
We are talking about the system.
The whole thing, the interface, the infrastructure, the data pipes. Because as we'll see, you can have the smartest, most state-of-the-art algorithm in the world, but if the system around it is flawed,
It's useless.
it's not just useless, it can be dangerous. It can bankrupt companies.
So let's jump right into the first big culture shock the book highlights, the massive gap between research ML and production ML.
Oh, yeah.
I love this comparison because it feels like the difference between a pristine, sterile laboratory and, well, a muddy construction site in the middle of a rainstorm.
That is a very, very apt analogy. In research, think academia or those famous Kaggle competitions. You're usually handed a data set.
Right, a nice little zip file.
Oh, a zip file. It's static, it's clean, it's historical. Your goal is very singular. Get the highest accuracy score on a leaderboard. You want state-of-the-art or soda performance.
You want that high score.
Yeah.
You want to beat the other teams by 0.001%, but then you move to production.
And suddenly the floor falls out. In production, the data is constantly shifting. It's noisy. It's missing values. And crucially, accuracy isn't the only thing that matters anymore.
Not even close.
In fact, sometimes accuracy is the least important thing. You have to worry about latency.
How fast is it?
You have to worry about fairness. You have to worry about profit.
Chip uses this incredible example of a restaurant recommendation system to show just how messy this gets. It's like a masterclass in office politics.
It is the perfect example of stakeholder conflict.
It really is.
So imagine you're building this app to suggest places to eat. You have the ML engineers. What do they want?
Oh, they're the purists. They want the smartest, most complex model possible. They want to predict exactly what you want to eat with perfect accuracy.
They want to use the latest transformer architecture they read about on Twitter yesterday.
Totally. They want to write a paper about it.
Correct. But then you have the sales team. Do they care about perfect accuracy?
Absolutely not. They want to recommend the restaurants that paid for ads.
Exactly. Revenue.
If the model recommends some hole-in-the-wall taco spot that doesn't pay fees, the sales team sees that as a failure, even if the taco spot is amazing.
Exactly. And then you have the product manager.
Right.
They're looking at user engagement. They notice that if the app takes 2 seconds to load because the model is so huge and complex, users just close the app and go to Google Maps.
They want speed, low latency.
And meanwhile, the infrastructure engineer is waking up at 3 in the morning because the servers are melting down trying to run this massive model the engineers built.
They just want to stop the production line to fix the scaling issues.
And sitting at the top is the manager who just wants to maximize the profit margin.
Which might mean firing the ML team if they cost too much in server bills.
Right. So in production, you aren't optimizing for a score. You're negotiating a peace treaty between all these people.
That's the key takeaway. In the real world, best is subjective. If a model is 99% accurate but costs 10 times more to run than a model that is 98% accurate.
The business is probably going to pick the cheaper one.
Which leads us to a story that I think perfectly encapsulates this whole accuracy isn't everything idea, the Netflix tries.
Ah, yes. The famous $1 million prize.
Legendary in the tech world. This was back in the mid-2000s.
Yeah.
So Netflix offered a cool $1 million to anyone who could beat their recommendation algorithm, Cinematch, by just 10%.
And teams from all over the world worked on this for years. It was like the Olympics of data science.
Right. And finally, a team won. They used this technique called ensembling.
Right. Ensembling is basically taking multiple different algorithms, sometimes hundreds of them, and just averaging their results.
Sort of like asking 100 different experts for their opinion and taking the consensus.
Exactly. It's a very powerful technique for squeezing out that last tiny bit of accuracy.
So they won the money. They got the big check. But here is the twist, and this blew my mind.
Yeah.
Netflix never used the full winning solution in production.
They didn't. Not a bit of it. And the reason ties back to exactly what we just discussed about stakeholders.
The engineering effort.
The engineering effort to keep that massive, complex ensemble running wasn't worth the tiny gain in accuracy. It was too complex. It would fail too often.
It was a $1 million solution that was too expensive to actually use.
A hard lesson.
You could be the best in the world and still be useless to the business. But this complexity brings up another scary difference between regular software and ML software.
Mm-hmm.
When regular software breaks, it's loud.
It is. You get a 404 error or a blue screen of death, or the app just crashes to the home screen.
You know something is wrong immediately.
The users know it. The developers know it.
The ML.
ML systems fail silently. This is one of the most dangerous aspects Chip highlights.
How so?
The function.predict will still run. The system will still give you a number or a recommendation. It will look like it's working perfectly.
But the answer will be wrong.
The answer will be wrong. So users could be getting bad advice or bad medical diagnoses or bad financial predictions for days or weeks.
Nobody would know.
Exactly. Imagine a pricing model for an online store. Maybe a bug causes it to price everything at $1. The model works. It predicts a price. The checkout works. You might not realize you're hemorrhaging money until you look at your revenue report a month later.
That is terrifying.
It's like a gas leak.
You don't know it's there until the explosion.
Which is why Chip emphasizes that monitoring is almost more important than the model itself. In traditional software, you test the code.
Right.
In ML, you have to test the data, the code, and the output constantly.
This connects to what Chip calls the data science hierarchy of needs. It's a pyramid concept, originally by Monica Rogati. I love a good pyramid diagram.
It's a great one.
So what's at the very top?
The top is the cool stuff. AI, deep learning, the glowing brain memes.
And that's what gets the funding and the press.
Right. That's what everyone wants to do. But it's the tiniest pick of the pyramid.
And the base.
The massive foundation is data collection, reliable data flow, infrastructure cleaning, and labeling.
It's the plumbing again.
It is always the plumbing. You cannot do the cool AI stuff if you don't have reliable data flowing in.
It reminds me of that great debate in the industry. Mind over data versus the unreasonable effectiveness of data.
Ooh, a fight. Yeah. So in one corner,
Yes, who's in which corner?
you have people like Judea Pearl, a Turing Award winner, basically the Nobel Prize of Computing. He says data is profoundly dumb.
Wow.
He argues you need causal reasoning, you need to teach computers to understand why things happen, not just look for patterns in massive piles of numbers.
And in the other corner.
You have Peter Norvig from Google. He famously said, we don't have better algorithms, we just have more data. His point is that simple algorithms with massive amounts of data often outperform complex algorithms with small amounts of data.
And Chip argues that in the production reality, the Google approach usually wins.
For now, yes. In the vast majority of business cases, you will get a bigger performance boost from cleaning up your data or getting more of it than you will from inventing a clever new algorithm.
It's unglamorous, but it's true.
So true.
There's that quote from Andrej Karpathy, who was the head of AI at Tesla.
Mm-hmm.
He compared his PhD to his work at Tesla.
Right. He said during his PhD, the data set was static and clean. He spent his time sleeping and dreaming about models. He was tweaking the math.
Love fun stuff.
But at Tesla, the data is constantly shifting. It's biased. The labels are wrong. He realized that 75% of his time was just dealing with the data mess.
So if you're listening to this and you want to get into ML, learn to love the mess.
Or at least learn to be a janitor for data.
Precisely. Speaking of messes, let's talk about the sneaky villain of machine learning. Data leakage. This part of the book felt like a mystery novel, where the detective realizes the killer was in the room the whole time.
Data leakage is fascinating because it's essentially the model cheating.
Cheating how?
It's when the model accidentally gets access to the answer key during its training. in a way that it won't have in the real world. And the model, being a lazy optimization machine, will always use the cheat sheet if it can find it.
And the example Chip gives regarding lung cancer detection. This one really stuck with me. Can you walk us through that?
Oh, this is a classic, tragic example of leakage. So researchers trained a model to detect cancer from CT scans. They gathered data from different hospitals, and in the training set, it worked perfectly.
High accuracy. They thought they'd nailed it.
Exactly. Pop the champagne.
Yeah.
But then they took it to a new hospital, Hospital B, and it failed completely. It was no better than a coin flip.
Why? I mean, was the cancer different?
No, it turned out that in the training data, there was a hidden pattern. The hospital where they got the data had a specific procedure. If a patient came in for a routine checkup, they used a portable mobile scanner, a bit lower quality. But if a patient was really sick and likely had cancer,
He got the better machine.
they were sent to a special room with a fixed high-res scanner.
Oh, no. I think I see where this is going.
You see it. The model didn't learn what a tumor looks like.
It learned that high-res image is cancer and low-res image healthy.
Yes, it learned to identify the machine, not the disease.
That is wild. It took the path of least resistance. It didn't look at the lungs. It looked at the metadata of the image effectively.
Exactly. So when they went to Hospital B, which maybe used different machines or didn't have that specific protocol, the model was lost. It didn't have its cheat code anymore.
And the scary part is, during training, the researchers thought they were geniuses.
That's the danger. The metrics look great. Leakage makes you feel good until you deploy. Chip mentions other forms, too, like time travel.
Wait, time travel. Now we're getting into sci-fi.
It's a lot less exciting than it sounds. If you are predicting stock prices and you randomly split your data into training and testing, you might end up training on data from next week to predict data from last week.
Ah, so you're using the future to predict the past.
Which works great in testing because the model knows the future. But unfortunately, in the real world, we haven't figured out how to get stock data from tomorrow yet.
Bummer. If we did, this deep dive would be very different.
So you have to split data by time. Train on January through March, test on April, never mix them. You have to simulate the constraints of reality.
This all circles back to a core theme Chip emphasizes: practical design. We have this obsession with SOTA's state-of-the-art. But the book argues that SOTA is often a trap.
It is a trap. Business leaders love it because it sounds cutting edge.
Well-
We utilize state-of-the-art AI. Sounds great in a press release.
And developers love it because it's exciting to use the newest model.
Of course. But SOTA models usually only prove they are better on static academic benchmarks.
Right. Just because it's good at recognizing cats in a massive generic database called ImageNet doesn't mean it's good at recognizing defects in your specific manufacturing line.
Precisely. And often these models are massive. They are slow. Chip brings up the Zen of Python here. Simple is better than complex.
I love that philosophy.
Yeah.
Why is starting simple so important in this context?
Well, three main reasons. First, it's easier to deploy. You can get a simple logistic regression out the door in a day and see if your pipeline works.
Get something working.
Second, it's easier to debug. If a simple linear regression gives you a weird result, you can probably look at the weights and figure out why.
Okay.
If a billion parameter neural network gives you a weird result, good luck explaining that to your boss.
It's just a black box. And the third reason?
It establishes a baseline. This is crucial. If you build a simple model in a day and it gives you 90% accuracy, and then you spend 6 months building a mega model that gives you 91% accuracy.
You just wasted 6 months for 1%.
Exactly. And you need to know that baseline to make that decision. Without the simple model, you don't know if 91% is good or bad.
And Chip points out that users often can't tell the difference anyway.
Right. From a user's perspective, 95% accuracy and 95.2% accuracy feel the same.
But they can tell if the app is slow.
They can definitely tell if the app is slow. So speed often beats that tiny bit of accuracy.
The real world.
Almost always. If Amazon recommended products with 100% accuracy, it took 10 seconds to load the page, nobody would buy anything.
This has been such a refreshing look at ML. It's less about magic and more about rigorous engineering.
That's the synthesis here. Designing ML systems isn't just about maximizing accuracy on a graph. It's about managing trade-offs.
Right.
It's about being a good software engineer, not just a good mathematician. You are balancing latency, cost, accuracy, and data quality.
It really redesigns what it means to be good at AI. It's not just about knowing the math. It's about understanding the system.
Which brings me to a final thought I'd like you to mull over. We talked about how models depend on data, but Chip hints at something deeper. Data dependency effectively means world dependency.
What do you mean by that?
When you write traditional code like, if by 5, do this, that logic stands forever. It is a logical truth. It doesn't change unless you rewrite the code. But an ML model, it depends on the data flowing through it, which is a reflection of the real world.
Okay, right.
So imagine you build a voice recognition system. It works great, but then the world changes. Maybe a new phone comes out with a much better microphone.
Or a new slang word becomes popular.
Or a global pandemic changes shopping habits overnight. Suddenly, the data input changes.
And the model might break.
Yeah.
Even though you didn't touch the code.
Exactly. The code didn't rot. The world changed. We are building systems that are organically tied to the whims of the real world. Is our infrastructure ready for code that rots? Not because of bugs, but just because user behavior shifted slightly.
That is a heavy thought. It's like living, breathing software.
Yeah.
It makes the job sound much harder than just writing code and walking away.
It requires a whole new way of thinking about maintenance. You aren't just maintaining code, you are maintaining